Okay, problem 5. So let's first let's first talk about the rotation. Okay, the rotation of a line. Let's first talk about the rotation of a line in a two-dimensional space. Okay, so let's say I have a line here. Okay, the length of this line is L. Okay, and I put it in XY coordinate. Of course, I will have this endpoint coordinate. Okay, let's call it X naught, Y naught. Right, and now I have an angle between the line and the positive x-axis. Let's call it alpha. Okay, now I rotate this line. Okay, I rotate this line. For example, after the rotation, the line is here. Okay, so what is not changed is the length of the line. It's still the same line, still the same length. Okay, however, this endpoint, okay, however, it's the endpoint, its coordinate has changed. Okay, let's call these new coordinates x1 and y1. Okay, and because you rotate counterclockwise, okay, here counterclockwise, because in this direction. But let's say the rotation angle is called theta. Okay, let's say the rotation angle is called theta. So now, let's first write down something we already know. X naught is the length of the line times cosine alpha. Right? It's this line times cosine alpha, right? That would be x naught. Okay, similarly, y naught is going to be this line times sine alpha. Okay, y naught, this length is this line times sine alpha. Okay, what about x1, right? After the rotation, what about x1? x1 is very simple. It's also length times cosine. However, now the angle is alpha plus theta, right? The total angle is alpha plus theta. Okay. All right, let's do this. So it's L, right? Remember cosine A plus B is cosine A cosine B minus sine A sine B. Okay, and what is that? It's L cosine alpha cosine theta minus L sine alpha sine theta. And here's the thing, L cosine alpha, right? It is exactly x0. L sine alpha, L sine alpha, it is y0. Okay, so that's x1. y1, very similar. y1, now it's right this length, right? It can be length of L times sine alpha plus theta. Okay, so it's L times sine alpha plus theta. Okay, so it's L sine, it's sine alpha cosine theta plus cosine alpha sine theta. Okay, it is the length of sine alpha cosine theta plus the length of cosine alpha sine theta. Okay, then L sine is y naught. Okay, L cosine is x naught. Right. Okay. So here, let's put them together. Okay, your x1 is x naught cosine minus y naught sine. Your y1 is x naught sine plus y naught cosine. Okay, and now we write it in a matrix form. Okay, the left-hand side x1, y1, we treat it as a column vector. And then here, the right-hand side, I can write it as a matrix product. It's cosine, negative sine. Okay, sine, cosine. Okay, times x naught, y naught. Okay, if I write it in this form, now everything is very convenient because if I know the original endpoint and I know theta, I don't need to do all this derivation anymore. I just need to do the matrix multiplication and immediately I will get my endpoint after the rotation. Okay, this is the line's endpoint before the rotation. This is the line's endpoint after the rotation. And I know the rotation angle is theta, then immediately I can get it. Okay, this is for this is for a two-dimensional case. Okay, and in problem 5, it is a three-dimensional case, which is very, very similar. Okay, it says, okay, one more thing. This matrix, we give it a name. We call it a rotation matrix. Okay, we call it a rotation matrix because we do the matrix product, we will get a new vector. Okay, it's a rotation matrix. So in problem 5, it's a 3 by 3 matrix. Right, and now our rotation matrix, you can see the first two by 2 matrix are the same. It's cosine, negative sine, sine, cosine. Okay, and here it's 0, 0, 0, 0, 1. Okay, so this rotation matrix, it will rotate the line in the three-dimensional space. Okay, it says it rotates a point about the z-axis by theta radians in counterclockwise direction. The important thing is, right? The important thing is now, if you rotate it about the z-axis, sorry. If you rotate it about the z-axis, wait, then the thing is, it does not, okay, I'll just copy. It does not change the z coordinate. Okay, let's see. So you rotate it around the z-axis, it does not change the z coordinate. It only changes its x and y coordinates. So let's say the original point is x naught, y naught, z naught. Okay, after the rotation, you'll get, right? So let's do the matrix product. It's this times this. Okay, it's cosine x naught minus sine, sorry, cosine theta x naught minus sine theta y naught. Okay, and then the second part is this times this. It's sine theta x naught plus cosine theta y naught. Okay, then this times this is just z naught. Okay, you can see this is your new x1, this is your new y1, this is your new z1. Okay, z1 is equal to z naught. Okay, so that means on this rotation, the z coordinate doesn't change. And x1 is this combination of x naught and y naught. You can see it's exactly the same. Right? Y1 is this combination. You can see it's exactly the same. Okay, it's exactly the same. So that's why this is a rotation matrix for the three-dimensional case. Okay, this is a rotation matrix for the three-dimensional case. Okay, now show R is invertible. Okay, let's work on it. R is invertible. So last tutorial, we've talked about a matrix is invertible if and only if the determinant of that matrix is not 0. Okay, it's not 0. So let's let's calculate the determinant of the matrix. Okay, now, of course, we want to pick a row with as many zeros as possible, so let's pick the last row. Okay, so the determinant is going to be 0 times, something. I don't bother write it down. Okay, let's try it. Let's write it down for practice purpose. 0 times -1 to the power of 3 plus 1, because it's the 3-1 entry, times the determinant after you delete the third column and the first row. Okay, so it's negative. Okay, in the exam, you don't have to write this. Here, it's just for the practice purpose. And plus 0 times the determinant of this matrix. It's -1 to the power of 3 plus 2 times the determinant of this matrix. And plus 1 times -1 to the power of 3 plus 3 times the determinant of this matrix. Okay. Right, so the first two parts are 0. Okay, this part is just -1 times 1 times here, it's cosine theta times cosine theta. Okay, minus sine theta times sine theta. Okay, so it is cosine theta squared plus sine theta squared. Okay, it's always 1. So you can see, for no matter what value we give to theta, it's cosine theta squared plus sine theta squared, it's always 1. So for any value of theta, this r is always, the determinant of r is always 1. Okay, it's always non-zero. Right, so that's why r is invertible. For any value theta. Okay, then find the inverse R inverse. Okay, so let's find the R inverse. R inverse. Okay, so for any matrix, if a matrix is, let's write down the formula. If a matrix, if an m by n matrix is invertible, okay, which you already know, that means the determinant of that matrix is not 0. Okay, then what is its inverse? Okay, we have a formula. The inverse is 1 over the determinant of that matrix times, right, times its cofactor matrix transpose times C transpose. What is C? C is A's cofactor matrix. Okay, what is transpose? Transpose, remember, it's row becomes column, column becomes rows. For example, if it's 1, 0, 2, 3, right? If it's transpose, then row becomes columns. So it's 1, 0, row become columns. Okay, and the column becomes rows, right? Column becomes rows. So that's the transpose. Okay, so this is a general formula. So in this case, right, we need to get R's cofactor matrix first. Okay, we need to get R's cofactor matrix first. So let's write everything down. It's going to be a 3 by 3 matrix. So the 1, 1 entry is -1 to the power of 1 plus 1. Okay, times, you delete the first row, you delete the first column, and these things determinant. Okay, this is going to be the 1, 1 entry. So let's do it. Okay, here it's going to be 1. Okay, this part is cosine times 1 minus 0 times 0. So the result is just cosine. Okay, so here the first entry is just cosine. What about the 1, 2 entry? It's negative 1 to the power of 1 plus 2 times, okay, after you delete the first row, you delete the second column, you get this, right? You get this entry. So it's sine theta 0, right? 0, 1. Okay, let's do the calculation. So it is negative 1. Here it's sine minus 0, so it's negative sine. Okay, so I think you can do the rest of it by yourself. Let's just do one more example. Okay, for example, let's do this one, right? The 3, 2 entry, it's negative 1 to the power of 3 plus 2 times. Now you delete this row, delete this column, so you get this. Okay, it's cosine 0, sine 0. Okay, now the determinant is going to be the product minus the product. It's going to be 0, so here we have 0. Okay, so for the rest of this question, you can do the same. You need to do this calculation by yourself. Sorry, this is... Okay, if you do it correctly, you'll get this. Okay, sine, cosine. Okay, 0, 0, 1, 0. Okay, do it correctly, you'll get this cofactor matrix. Okay, so don't forget about transpose it. Now we want to get R inverse. Okay, let's write it down here. Okay, now we want to get R inverse. R inverse is a determinant of R, is 1 over the determinant of R. Just now we've already figured it out, right? Determinant of R is 1. Okay, times C transpose, right? Must transpose. C is here, must transpose it. Okay, how do you transpose? Row becomes column. First row becomes first column. Okay, row becomes column. Second row becomes second column. All right, row becomes column. Third row becomes third column. Okay, must transpose. So you can see here, the difference is very subtle. Right, here it's sine, here it's negative sine, here it's sine, here it's negative sine. So you must transpose C. Okay, that is a formula for the inverse. Okay. Here is the last step. This determinant is just 1, right? So the determinant is just 1. So R inverse is equal to this matrix.